Hello students, we'll continue with in-class exercise 2 for Arenes. So for this particular in-class exercise, you are given two structural elucidation questions. I think they should be worth between 5 to 10 marks. Yeah, so this is usually the range of marks you expect for structural elucidation when you are in JC2 for a typical H2 curriculum. Yeah, so this is unlike the olden days in the 90s or early 2000 where it's possible for you to get an elucidation question, say between 12 to 20 marks. Yeah, but for the current syllabus, this is not likely to be the case. Okay, so let's just dive straight in. So we have compound A with the molecular formula C8H8. Let's try to calculate the degree of unsaturation. So 2n plus 2, so that will be 18 minus 8 divided by 2. So you get a degree of unsaturation of 5. Yeah, usually for a degree of unsaturation of 5, it tells you that 4 of it is likely to due to a phenyl ring. Okay, to be a phenyl ring. Okay, and then the other one, it could be a CC double bond or a ring. Okay, just a normal alkyl ring or cycloalkyl ring. Okay, but we can easily conclude based on the information given to us. Okay, so the second line reads, when the solution of bromine in CCl4 is added to A, it decolorizes immediately. So this actually tells us that the CC double bond is likely to be present instead of the ring. Yeah, and this particular reaction is likely to be an electrophilic addition. Okay, but of course, if you did not calculate the degree of unsaturation, you will not be able to conclude how many CC double bond you have in the side chain. Yeah, but of course, in this case, you know that you have 5 degrees of unsaturation, 4 of it likely to due to the phenyl ring, 1 of it beyond the phenyl ring. So of course, you can conclude that there's 1 CC double bond. Yeah, there are other clues along the way which helps you to conclude that there is 1 CC double bond. So for example, this particular clue, 1 mole of A reacts with 1 mole of hydrogen in the presence of platinum to give you C8H10. So this actually tells you that there's an increase in hydrogen from 8 to 10. Yeah, so this further confirms that there is 1 CC double bond present. Okay, so just once. And if you recall from earlier videos, right, the addition of hydrogen is known as catalytic reduction. Okay, it is not electrophilic addition. So when you're writing, when you're drafting out the table of information of and deduction, you have to mention that the reduction via using 1 mole of hydrogen is known as catalytic reduction, and it tells us the presence of 1 CC double bond in the side chain. Okay, then beyond that, the next clue we have is on heating A with acidified KMnO4 and subsequent cooling, I'm actually getting a crystalline solid with the formula C7H6O2. So if you were to calculate the degree of unsaturation of C7H6O2, 2n plus 2, 16 minus 6 divided by 2, you get 5. So you realize that the phenyl ring is retained. Okay, so there's nothing happened to the phenyl ring. And then you notice that if I have a benzene ring with side chain in the presence of acidified KMnO4, so you would expect some form of side chain oxidation. And in this case, you know that there's a C double bond. So beyond the side chain oxidation, you are probably expecting some form of oxidative cleavage of the CC double bond. Okay, so anyway, you get a crystalline solid B with 2 oxygen, 5 degree of unsaturation. The final degree of unsaturation is likely to be due to the presence of a C double bond O. This C double O is likely to be part of the carboxylic acid. Okay, so how can we conclude that? Maybe we can try to use this particular method of doing. So you have 8 carbon in total. So you have that means that your side chain will contain 2 carbon. Then after side chain oxidation or oxidative cleavage, you're only left with 7 carbon. So that means that one of the carbon is lost as CO2. So it is likely that your unknown is mono substituted as well. So with this information, I can just write C7H6O2. And I know that since my unknown is mono substituted, let's call this R. So this portion of the phenyl ring, the formula is C6H5. So I just subtract off C6H5 from here. Okay, then I will be getting CHO2, which fits perfectly well to the formula of my side chain over here. So therefore, I can easily come up with the structure of B to be benzoic acid. So therefore, the structure of B, I will be able to conclude it to be benzoic acid like this. Okay, yeah. So we can further confirm later on, but we'll just move on. So I've covered the one I've highlighted in orange, so I'll just move on. C shows no apparent change when liquid bromine is added. Okay, so in that case, you notice that there is a contrast between A and C. Yeah, so if A undergoes electrophilic addition, and that is likely to be due to the presence of a CC double bond, that means that the CC double bond, the pi bond, is no longer present in C. Yeah, so we can easily conclude this because liquid bromine is not going to react with C. However, it gives a dense white fumes when liquid bromine is added in the presence of a little iron powder. So this seems to indicate that electrophilic substitution is occurring. Yeah, so the purpose of the iron powder is really to react with the with the liquid bromine to generate FeBr3, and then in the process act as a Lewis acid for electrophilic substitution to occur. Yep, and the dense white fumes here is likely to be HBr gas. Okay, so with all these detail, I think it's quite obvious that the structure of C is likely to be a phenyl ring, and then with an ethyl side chain. And of course, when bromine is added together with iron, electrophilic substitution occurs at the one of the position. In this case, it's likely to be the second or the fourth position. Okay, and of course, the structure of A is likely to be a phenyl ring with a double bond at the side chain. Yeah, so this is phenylethene. Phenylethene. Okay, or its common name is known as styrene. Okay, if styrene doesn't ring a bell, I think you might have heard of polystyrene or expanded polystyrene, which is the substance responsible for making your styrofoam box. Okay, yeah. Please take note that I am explaining the thoughts process in going about getting the answer. So of course, in real exam, this is not the way you should present your answer. In real exams or in the actual exam, you should be presenting your answers in the form of a table of information and deduction. Okay, so all these deduction which I'm explaining to you, it should be incorporated in the table. Okay, and of course here you're supposed to write the balance equation where appropriate. So I'll just attempt to write, say, two of them, the two most cumbersome ones. So for example, side chain oxidation, we have a polyethene here, and then usually we represent the oxygen with bracket O for organic chemistry. So I'm going to draw in the benzoic acid, and then one of the carbon is lost as CO2, and then of course if you count the total number of H's, you have 6 H here. On the left hand side you have 8 H's, so one of the H is lost as H2, two of the H is lost as H2O. So if you do a quick count in the O's, you have 1, 2, 3, 4, 5. So therefore the number of O's here will be 5. Okay, so this is how you write a balance equation for side chain oxidation. I think the rest will be relatively straightforward. Maybe for electrophilic substitution, I can also show you how to write it. So I have a side chain here, which is an ethyl side chain. So this is structure C plus Br2. So I don't have to write the Lewis acid catalyst here, but if I want to, I can. Okay, then I'm going to end up with either second position or fourth position substituted. I'll write it as fourth position plus HBr like this. Okay, yeah. So that's the end of the review for question 1. I'll move on to question 2 now. Okay, so for question 2, I have two structure L and M, both with formula C9H10. Okay, so I have C9H10 as the formula for both L and M. Okay, so I'm just going to write it over here. So C9H10, C9H10, and that's M. Okay, so both reacted with KMNO4, KMNO4 alkaline condition, followed by acidification. Okay, so this is 1, and then 2, acidification, and just add H plus. And of course, this is a hot condition. And then I will end up with benzene 1,2-dicarboxylic acid. Okay, so I'm ending up with benzene 1,2-dicarboxylic acid like this. Okay. So the first thing we might want to do is to calculate the degree of unsaturation of L and M. So the degree of unsaturation in this case 2M plus 2 minus 10 divided by 2. So that will give me 5 degree of unsaturation. So 5 degree of unsaturation, one of it is of course due to the phenol ring. 4 of it is due to the phenol ring, because we already know that my final product is benzene 1,2-dicarboxylic acid. And then the remaining one, again, same story. It could be a CC double bond or a cyclo-alkyl ring. Okay, could be a cyclo-alkyl ring as well. Yeah. So how do we know which is which? Well, very simple. You are given the clue over here. So L reacts with aqueous bromine, but M does not. Now, if they tell you that L reacts with aqueous bromine, but M does not, then this is a super huge clue which you can use. Because if I look at the product N, right, let's do a quick numbering. 1, 2, 3, 4, 5, 6, 7, and 8. You notice that one carbon is missing. So the carbon that's missing is likely to be lost as CO2. Okay, so this is likely to be carbon number 9. Yeah, so that means that because L reacts with aqueous bromine, okay, so therefore L must contain the CC double bond. So my CC double bond in L will either be part of carbon 8 or part of carbon 7. So therefore the terminal alkene will be bonded to carbon 8 or carbon 7. So it's up to you to decide which carbon you want. So in this case, for convenience, I will just bond it to carbon number 8. So I have a benzene ring here, and then this is carbon number 8, carbon number 9, and then carbon number 7. Okay, so that will be 6, 5, 4, 3, 2, 1. Okay, so this particular structure is likely to be L. Okay, it fits all the information. 5 degree of unsaturation, C9H10, a CC double bond which will react with aqueous bromine. Okay, so for M, because it doesn't react with aqueous bromine, so therefore N must contain a cyclo-alkyl ring. So therefore the structure of M will be very similar to L, except that I will need to link up carbon 9 and 7 with a single bond. So in this case, 1, 2, 3, 4, 5, 6, and then 7, and then 8, 9, and then I link them up with a single bond. That will be 8, 9, 7. So this is cycle alkyl. So it can also undergo side chain oxidation in the presence of oxidative cleavage condition. Okay, and then 7 and 8 will end up to be the carboxylic acid, and it doesn't react with aqueous bromine because it doesn't react with electrophile without a Lewis acid carrier, because 897 essentially is an alkyl side chain, and of course the benzene ring, you need a stronger activating group in order for aqueous bromine to react with it. Yeah, so therefore it fits in all the information. Some of you might ask, is there an alternative answer? Yes, so it is actually possible for my phenol ring to be a 6-membered ring, and then my 8 and 7 to be bonded directly. So this will be 7 and 8. And then of course either 7 or 8 will have one of the alkyl side chain like this. Yeah, so this is also a possible alternative answer to M. Okay, so I hope you find this particular review video interesting, and I mean, helps you in understanding how we come up with the answers to in-class exercise 2. Okay, yeah, do look out for future videos on either the lectures coming up or the rest of the in-class exercises.